Hello, everyone. Good afternoon. I'm really glad to be here to meet some of the Seele fans in this premium location. I heard Tiger told me that some of the people, there's one people from Mexican, and there are a couple of people flew from China, and also people from San Diego. There are also a lot of people from different places. I just really want to say, firstly, that thank you very much for joining us. The Seele team really appreciates that. Dr. Zeng has already talked about a lot of ideas about Seele, including the money part. From my perspective, I'm going to talk about more about Seele from the technical side. But in 2008, when the credit crunch happened, I was actually in London. The label of the credit crunch was actually the day Lehman Brothers went bankrupt. The day before Lehman Brothers went bankrupt, I remember clearly that the credit rating for Lehman Brothers was very, very high. And suddenly, the second day, Lehman Brothers went bankrupt. So this is how embarrassing a centralized system can do, and how unsafe a centralized system can be. And later, after a few months, in January 2009, Satoshi actually created his first block, the Genesis block, on the blockchain with the headline from the Times saying that the chancellor on brink of the second bailout for the banks, which was quite a joke. But because of this, because the blockchain was created just after the credit crunch, so some say that the creation of blockchain and the creation of Bitcoin was actually inevitable. After that, I actually have a continuous road like that. I just hope later I have videos and they're gonna display fine. But after the Bitcoin, the famous Vitalik actually created the famous product Ethereum, which comes with a smart contract, which really enhanced the features of blockchain technology. Then after Ethereum, there has been a lot of products coming into the market, and they are looking at different features and different problems. But until today, although we do have so many products in the market, but there still seems to be a lot of unsolved problems. So what I really want to talk about today is the current problems and the challenges about blockchain. And what I really want to talk about is actually what Seele proposes and how Seele is going to deal with these problems. But the problem that people care about the most is firstly the performance. Dr. Zeng already mentioned at Bitcoin is about 7 transactions per second. It's very low, but we have a lot of other products which has better TPS. But the performance also include other factors like the confirmation delays, this kind of stuff. And people also talk about the scalability and mining issues. And there's another problem I would like to talk about the lack of large-scale applications using blockchain, which maybe not many people have thought of this. There has been an enormous amount of effort trying to deal with the problem, including algorithms and products. POW, everybody knows POW works quite well with Bitcoin, and it's been running fine for the last 10 years, so it's very secure. And in fact, Ethereum is also using POW, but the problem for POW is that it's actually quite slow. And for PBFT, this consensus algorithm has been well established already, and there's many academic papers about explaining PBFT. But PBFT works really well for small-scale network. But when the network scale gets big, the performance of PBFT reduces significantly. And we have some other products which I listed here. I think they have some particular features. Like in Zilliqa, they use a technology called sharding. And with sharding, you can distributed the transactions into different shards or different locations. So this will increase the performance of the Leica. But there seems to be some problem because the transactions are distributed into different places. So when you do the cross-shard transactions, it becomes slower. And IOTA and some other products uses technology called directed acyclic graph, which is essentially not a blockchain. But with DAG, it's actually increased the transaction speed a lot. But DAG seems to have a problem in dealing with a double spending problem. And the famous EOS, actually, I think everybody knows, using the DPoS method, which have really good performance. But because the DPoS actually uses a small group of selected delegates to do the consensus, so it's not, it actually compromises decentralization. Okay, let's have a quick look of the Seele framework. So what Seele look like is like this. The Seele framework actually contains a lot of components. So from top to the bottom, we have the decentralized application layer. So this layer, we provide standard tools like the wallet, browser, blockchain monitor, transaction monitor, ID stuff. And with the smart contract, we actually designed a very special smart contract using knowledge engineering. And the smart contract is also designed for non-programmers. And the smart contract is also compatible with Ethereum smart contract and also leveraged with the mainstream programming languages like Go, C++, Python, these kind of languages. But we actually didn't talk about smart contracts in our white paper. Later, I'm going to show you an example of our smart contract. From the consensus algorithm, we developed a very special neural consensus algorithm. Today, I'm going to focus on the EDA algorithm, which we developed, and what's the theory of EDA, how does it work? And then we have some supporting features here, like the heterogeneous forest network and the data privacy and ownership. I'm going to quickly cover these. And in the very bottom, we actually have our network protocols. And these protocols actually support almost all of the layers above. So fundamentally increases the performance of the Seele blockchain. Consensus mechanism or consensus algorithm is considered or arguably considered to be one of the most important technology in the blockchain field. So the first question I want to ask is, can we have a really good consensus algorithm that supports large-scale network or not large-scale system like millions of nodes? Also with high performance, high concurrency, and high security, and also without compromising the decentralization. That actually sounds too good to be true, right? But I'm telling you that everybody sitting here today, we are all using this kind of consensus system every day. And the answer, you already saw it, is our brain. So everybody here has a brain, right? So the brain is highly efficient, and we can do a lot of stuff in parallel. Like I'm talking here, and I'm looking at you guys, and I can see that a gentleman in the back is stretching his legs. And I'm sure everybody has experience of playing your mobile phones while you're in the restroom doing stuff. So the brain is highly efficient, and you can really do things in parallel. So how does the brain work, right? So to you guys, my brain is actually a centralized system. But within the brain, there are millions and billions of cells, billions of neurons. There are approximately 14 to 30 billion neurons in the cerebral cortex. So to really send orders to my body, to really control my body, is actually these neurons sending the orders. But how does the brain, how do these vast amounts of neurons collaborate? How do they make a consensus just in a blink of second? So this is the question I want to ask. Of course, the brain is extremely complex. So what we think we learned are the three most important mechanisms from the brain. The first one is called feedback excitation. So every neuron actually have this kind of mechanism. So it uses the feedback from the previous response and then improve the next response. So this kind of mechanism, we can call it a learning mechanism, and it has already been borrowed and learned by the artificial intelligence scientists in the deep learning field. And then the neurons actually talk to each other in a peer-to-peer fashion, but each neuron only talk to a few neurons, not all the neurons in the brain, only talk to a few neurons, maybe surrounding to that neuron, but then those neurons also talk to the other neurons in turn, then talk to the other neurons in turn. So the communication network or the communication path actually becomes a tree-like structure, and we call this a neural tree. With the function of the neural tree, although one neuron only talks to a few neurons near that neuron, but it actually gets a large picture of the whole system. That's very interesting. So it gets samples and it only talks to a few neurons. Then it gets a big picture of the whole system. And the third one is actually a little bit difficult to explain. We say it's probabilistic consistency. That means with all these neurons, all the neurons working together, not all the neurons working together, there might be some neurons that maybe performed wrong or sending wrong information. But with the majority of neurons sending the correct information, then the system can observe what's really like for the whole system. And this experiment can be repeated like what we did in the statistics. And we say the probability of getting a similar result or same result is very high each time when we repeat this experiment. So we say when the neurons working together, we get a stable observation, and the result is statistically consistent. So using this kind of mechanism, we actually developed our epsilon differential agreement. And we use it as a consensus algorithm. So in our EDA algorithm, we actually have several rounds in the EDA algorithm. And each round we use the result from the previous round as an input, and then to improve the result for the current round. So that's like the neuron feedback excitation in the previous slides. And also each node in the system only talks to a few other nodes, and then these nodes talk to a few other nodes. This is like the neural tree in the previous slide. So with this kind of tree structure, one node only talks to a few nodes, then it can get a much bigger picture of the whole system. And then the experiment with majority of nodes working together, this experiment can be repeated and the result is statistically significant. So we can use EDA again and again and again. So this is the theory behind the EDA. So what actually does EDA do? Let me show you another example here. To really understand how the EDA do the work, we have to really look at what a blockchain does. So imagine if we have two blocks, block 1 and block 2, and block 2 actually links block 1 using the hash value calculated from block 1. I think everybody blockchain knows this. So fundamentally, what's the difference between block 1 and block 2? What does it establish? So the difference between block 1 and block 2 is that there are many transactions in block 1 and there are many transactions in block 2. Once you link the two blocks, the transaction orders are actually fixed. So all the transactions in block 1 actually took place before block 2. So fundamentally, what's important is to establish the transaction orders. So in EDA, we actually every node in EDA is calculating the transactions orders directly by using the information from a few other nodes. And Once the calculated result is smaller than a predefined value epsilon, we say the system is in a consensus state. So because in EDA, every node is only using the information from a few other nodes, but not restricted by the information from the previous blocks or from the previous transactions. So it looks like the computation is rotated, the chain can be rotated 90 degrees, and EDA projects the orders onto the x coordinates because they can do calculations in parallel. And because they can do calculations in parallel, so this allows the system to be, the performance to be increased significantly. So what is the actual task for each node in EDA? So let me give you another example, right? So imagine if we have two transactions here. Transaction 1 is labeled by the blue color, and transaction 2 is labeled by the red color. And imagine if we have 6 nodes in the system. This is the original state of the system. And each node have the 2 transactions. So in total, there are actually 12 dots in the original state. But the reason those dots are all in different places is because the system is not in a consensus state. So the task is to reorder these transactions in a way that the system, the 6 nodes all agree the 2 orders for the 2 transactions. So what EDA does is actually, imagine we have we only list a task for 1 node here. So it gathers information probably from 2 other nodes. And what it does is to calculate a most balanced value for the information it received. For example, if I have 3 values, I receive 3 values from 3 of you guys, and I can simply do an average function, right? So the average I calculated will be the closest value to all the 3 values. So as simple as that. But we can pick a statistic function here. We can use average, we can use the square root, we can use median, and these functions statistically have the stats advantages. So you can see only after 1 round of EDA in the 3rd figure, the result already looks much more organized than the original state. So after 1 round of EDA, it looks like this, and the purpose is that you can repeat it for several rounds until the value you calculated is smaller than the value you predefined, which is specified by epsilon. Then the system is considered to be in a consensus state. So let me show you another example of what EDA actually do. So this picture shows about 30 transactions labeled by the different colors. And on the x coordinates, we have in total 18,000 nodes. So the x coordinates is node ID. So each integer is 1 node. If we go up, each node have 30 transactions labeled by these different colors. So the original state looks really in a chaos state because when we do the simulation, we make it completely random. So the system is not in a consensus state. So the purpose is to use EDA to reorder the system. So let's look at the simulation. So you can see as we go to the 1st round, 2nd round, and 3rd round, last round, and the system, the order of the nodes becomes the same. So this is a working example of how EDA actually works. And in this simulation, we actually simulated 10 fault nodes in the diagram. And I think it took 4 or 5 rounds for the system to reach the final consensus. And you can do this parallelly with all other nodes or other transactions specified previous, you can define these parameters. And this slide actually shows a schematic diagram for the performance between 3 different consensus algorithms, the PBFT, POW, and EDA. PBFT, I already explained, it works quite well for small-scale systems, but for large-scale system, when you go right, the scale goes large. PBFT doesn't perform really well. The complexity of PBFT is in the level of n squared because it normally requires full node network communication. And POW actually looks really good. When scale goes bigger, POW looks like a straight line. But everybody knows that POW always takes long to finish, so it's actually really high. And with EDA, we actually, when you adjust EDA works quite dynamic and with a few parameters. When you adjust the parameters for every different scale to the most optimum option, we see EDA actually performs better than the diagonal line. So EDA actually supports large-scale system very well. And maybe I would like to talk about the famous DPoS from EOS, the famous DPoS algorithm. We haven't drawn it here, but I think DPoS is very efficient. But because it only uses selected nodes, so it compromises decentralization, but I haven't drawn it here. But I think it will be in the range of somewhere here or even below the EDA because it only uses a few selected nodes. Okay, so this picture shows the sampling effect for different scales. So if we divided the picture into half, the system on the left have 2,000 nodes, and the sampling distribution looks like that. And the picture on the right have 20,000 nodes. And with EDA, we can do the sampling for both systems, and you get a curve like that, you get a curve like that. And what we want to point out here is that you can see this looks like more similar to the original example. As you can see clearly for the histogram, this looks different, but the histogram between here and here looks the same. What is the reason for that is because the more nodes you have in the system, you actually have more samples. And EDA is actually using stats function to do the sampling. And in statistics, we know that the more samples you have, the more confident your result will be. So that's why we say EDA is actually performs really well for large-scale systems. Okay, so I give you another example to explain the effect of coverage for different scales for a single node. So the picture on the left shows that we have a system to have 20K nodes. The picture on the right shows we have a system for 200,000 nodes. So the coverage means the coverage for a single node means we only want to get one node. And how does the node cover the whole system? Remember, the nodes communicate with other nodes in a neural tree style fashion. Let me show you the simulation. So you can see the system on the right only take 3 rounds to reach the whole coverage for the whole system. And the system on the right is the larger scale system that have 200K nodes. And as for the smaller scale system, it actually takes 5 rounds to cover the whole system. That again shows that EDA actually works really well for large scale systems. Okay, my last slide about EDA actually shows the performance between confirmation delay, the sampling ratio, and the fault tolerance rate. So if we keep the sampling ratio fixed, then as we increase the malicious node, we got more delay. However, if we change the sampling ratio, we can see as we increase the sampling ratio, we have a larger fault tolerance. And this fault tolerance is even better than what we actually wrote in the white paper. It is actually very close to 50% from the simulation. And as we increase the sampling ratio, we also have a significant reduce in the confirmation delay. So just a quick recap of our EDA. EDA is a consensus algorithm, and it is inspired by how the brain works. So EDA actually employs statistics function to do the calculation, and EDA has a customizable consensus parameters. It supports high concurrency. high fault tolerance rate, and also is specially designed and to be suitable for large-scale applications. What is interesting is that EDA has customizable consensus parameters. So when you actually have a hand of play, maybe after we publish our mainnet, you can further customize your EDA algorithm, customize the performance and the fault tolerance rate based on your needs, based on your business. Okay, I talked about these issues already, right? People say blockchain is disruptive. People say blockchain is revolutionary. But we don't see a lot of large-scale applications using blockchain. We don't see many industrial applications. We don't see enterprise applications using blockchain. The use case we see the most are actually using blockchain to do cryptocurrencies, to do SEOs. Why don't we see a large, say, medical application or healthcare application? In fact, we know some companies that are trying to convert their infrastructure to blockchain. They spent millions, but they simply failed. And then they blame that because of blockchain technology, they have performance issue. We already explained the performance problem, and we provided a mechanism, a EDA mechanism we think is highly efficient. But we do think there's another factor that causes industrial application or large-scale applications that cannot be used in the blockchain. A factor maybe not many people have thought of. So firstly, you all know this is a network structure for blockchain. It's a peer-to-peer network structure. This structure works really well for blockchain, right? It's everybody has a distributed ledger here, and it works well for blockchain. But what is the need for industrial applications? What is the need for large-scale applications? For example, for the industrial applications, they have to serve for the society, right? So they have to be part of the society. So what would the requirement for the society? What is the society structure, and what is the structure for the social governance? So the structure for the society must look like this. The structure for the society shouldn't be completely peer-to-peer, nor should be completely parallel. It must have layers, and the layers must be conditional connected. This is the society structure we're familiar with. So if we really abstract the structure out, we get the logic structure, and this actually looks like a tree. Remember, I showed you before the neural tree structure. So is this a coincidence that the structure we get looks similar as the neural tree structure? The neural tree structure was because of the millions of years of evolution of the neurons. And it must be perfectly optimized for the neural tree structure. And the society structure is also because of years of evolution. So there must be similarities. So that's actually why we developed our heterogeneous forest network. So in the network, you can have education, you can have healthcare, you can have maybe finance sectors, and under education, we probably have universities, research institutes, and so on. And the universities, say, we may have Stanford. I think we have people from Stanford here. We may have UCLA, Berkeley, etc. So this is actually represents the society structure. And if you are a real large industrial application, probably you can be somewhere here, and you join the society, you provide your services. So in the forest network, we don't call it branches, we actually define the names for the partitions. We call them domains. So for example, if this is Stanford University, this might be UCLA, and under Stanford University, the leaves might be computing school, the law school. The reason we have this structure, you can see a clear advantage is that, say, this is Stanford University. And Stanford University have its own domain here. It looks completely separated from the UCLA University here. So it's actually, the Stanford University can run separately, or the computing school can run separately with the law school. In other words, this kind of design have really good resource isolation and have really good isolation of the resource and good performance, and also ensures high security because you can run independently. And in other words, that also means you can run in parallel with other organizations from different domains. So because you can run parallel in different domains, so the whole tree structure actually increased the performance of the whole network. And then what if you don't want to run in parallel? You don't want to run independently. Now the law school want to have a match, basketball match with the computing school, right? Because there are two parties, right? Now effectively you are doing collaborations. Although you are doing a basketball match, it's kind of a competition, but probably you need to find a third party to kind of, three parties to kind of doing the match together. So in case there's a dispute, you have a third party here. You can always find the other parties to join your collaboration. You can always find more parties, but the difficult part is to find the smallest necessary parties in terms of technology. So when you do collaborations in the forest network, it's effectively doing a consensus in the forest network. And because this is a tree-like structure, so we can use the technology from the computing graphic technology, and we just find the minimum graph cut, then we get the minimum participants needed. Then we can do collaboration between these parties. And when we do collaborations, we can use the EDA algorithm before then to do collaborations. And with this kind of collaboration, then there might be other collaborations in other domains, and those collaborations and those individual domains, as long as they don't intercept, they can do stuff in parallel as well. So the collaborations can also be done in parallel. The tree structure actually also ensures that when you do the collaborations, you have very good performance for the whole network. And in the heterogeneous forest network, we also define 3 roles: data, computing power, and algorithms. We think these 3 roles are the roles that have values in the future. So we think these are the roles that have value in the future. So because they have value, so the value can be exchanged in the forest network. So what's the advantage of defining 3 roles that have value? Imagine if we have an AI company that looks at, that's one training algorithm to detect the lung cancer. So traditionally, you need to buy a lot of servers, right, to train your algorithm. And also, you need to buy a lot of data from hospitals. So even before you train your algorithm, you actually spend a lot of money buying these servers and buying these data. And needless to say, the data from the hospitals will be very expensive and will be very difficult to get the data from the hospitals, because the data from the hospitals are very sensitive information. So how do we do it in the forest network? Because in the forest network, the data and algorithm and computing power are defined to have value. So you can effectively transfer and exchange these values in the forest network. So now for the AI company, they only need to focus on their algorithms, and they buy the data and ask the data to run on the computing power role. And then after they finish the computation process, the algorithm is done, and the computing power is released. So now the AI company only spend very little money, so they can do the work very, very fast, and they get their algorithm. This actually allows that everyone or every company to be a platform. So that means you only need to do your core business. And when you want resources, you just go to the heterogeneous forest network. You don't need to build them from scratch by yourself. And then you can exchange values using other data row or computer power row or algorithms row. Of course, there is another problem here, is that the data from the hospital is still very sensitive. So what we did in the heterogeneous forest network is that we actually created a value transfer mechanism. So when you do the computation for the sensitive data, we provided a secured sandbox environment, so the data will not be reviewed, and the computation is done within the sandbox environment. When the computation is done, the data is destroyed, and the computer power is released. So to ensure the data owner always have the ownership of the data. So this is the way we construct the new applications. Is we call the process construction development. Just like how you build a house, you buy stuff, you buy different components, and then you quickly build the house. And this is what I promised earlier, that I'm going to show you the smart contract. This is what our smart contract looks like. This is a non-programmer friendly version. So this is actually a proof of concept done by one of our partners using it in the healthcare industry to solve some problem. I'm not going to tell you more about this. We're going to publish it on our website later. But effectively, the doctors have their knowledges, and they are building a medical decision support system. And they are using a lot of different resources, including artificial intelligence and even the smart, this is a smart toilet, data from hospital, and they can build the system really, really fast, because now they only need to focus on their core business, and they can transfer data in the forest network using other resources. So this really improved the performance of building a new application in the forest network. So a short recap of the functions of the heterogeneous forest network. Heterogeneous forest network, the structure of the heterogeneous forest network matches the structure of the society, and it supports resource isolation, collaboration, and thus it allows large-scale applications to be implemented in the network. It also defines 3 roles that have value: the data, the computing power, and the algorithms. So everybody and every company becomes a platform, and it greatly increased the overall performance of the whole network. I've talked about the heterogeneous forest network and our neural consensus algorithm. And we also developed something in the very low level, our network protocols. So the network protocols will support our neural consensus algorithm, the heterogeneous forest network, and all other features in the Seele from the really low level. So similarly, like the internet protocol model, we developed our value network protocols model. So in the transport layer, we actually developed our transport protocol, value transport protocol, and QVIC protocol. These 2 protocols will really be optimized for the high-frequency transactions, and it enhances the performance of the EDA algorithm, for example. And in the application layer, we developed our value HTTP protocol and UAI protocol, and these are used for the ease of value transfers and navigations of the heterogeneous forest network. Okay, in summary, I talked about a few features about Seele: the neural consensus system, the forest network, the protocols mentioned about smart contract. There are also a few other features in the white paper that I haven't talked about. In fact, we also have a lot of new ideas. Seele always have a lot of new ideas. some of the ideas really increase the performance of the blockchain, we think. And some other ideas are bold enough to say that they guide the way the society works. Maybe not all of these ideas are perfect. In fact, no company can say they're perfect, right? But we do think our ideas are very novel and very innovative. And we will really work hard to implement our ideas and deliver our products. We think today, Seele is the pioneer of blockchain innovations. And we think tomorrow, Seele will really lead the future of blockchain development. Thank you, everyone.